I'm Scott Hollister. I'm actually professor in biomedical engineering, and I have joint appointments in mechanical engineering and also surgery in the medical school. I did my PhD in bioengineering. I'm alumni of the university. Right now we're in my laboratory at the University of Michigan in the Department of Biomedical Engineering. This is where we design and fabricate and what we would call functionalized biomaterials to do tissue reconstruction. So we can take actually patient image data like CT scans or MR scans, design a degradable device directly from those scans. We can build that from a biomaterial that will actually degrade in the body. Once we build this material, then we can add proteins or even genes or the patient's own cells to this material. We can implant that material within a defect within the patient, and then our goal is for that construct with the biologics, the cells and the genes and the proteins to accelerate natural tissue healing within the body. The scaffold will provide some temporary function within the defect, and then over time that scaffold will essentially degrade and the patient will be left with normal tissue. So that's the focus of our research in it, and we can do this for a wide range of applications. So in craniomaxillofacial surgery, this is one of our ideas to reconstruct large defects in the mandible. This is an application for cervical spine fusion. So again, you would fill this with cells or proteins to accelerate bone formation for healing. This is an application we're doing with pediatric otolaryngology with Glenn Green, and there's a condition where you have collapse of the trachea. So the idea in this case is you would like to take this structure, we call it tracheal splint, place it around the trachea, and we've designed needle holes into this so the surgeon can actually suture the trachea to this structure, so Glenn can do this, and it holds the trachea open so the patient can breathe. We can show you where this is our facility where we actually build the structures from the polymer that I talked about. This is essentially what people would call a three-dimensional printing system. You can see our designs are actually on the console here. We can put many different designs in this build platform, and we build very complex three-dimensional structures on a layer-by-layer basis. So this arm is going to sweep loose powder across. The laser beam, it'll be hard to see it, but it'll actually go and track the design from the computer file, and it will keep doing that until it builds the whole three-dimensional structure. So the advantage of this is we can build very complex patient-specific designs. We can build them fairly rapidly. It might take 2 to 3 hours to build all of these structures. So one of the reasons I think this is rewarding for us and what motivates us is a lot of people, faculty such as myself, go into biomedical engineering because they like the engineering, the technological aspect of it, but they want their application to be something that can directly, obviously, impact or improve people's quality of life. And we feel that this technology can help advance medical treatment. And again, the collaboration between the surgeons and the engineers allows us to create treatments that couldn't be created by either group alone, I think. So I think it's very rewarding overall, and that's sort of what motivates us at the end of the day.